Great. Welcome everybody to tonight's Deep Learning Adventures meetup. I'm gonna go ahead and share my screen and introduce our couple of things that we have going on. All right. So if you're not familiar with us, we have a lot on our meetup page in the About Us section. And included there are all our announcements and links to a lot of collection of videos and code repositories from our past meetings. We often do a course together or a coding challenge together. And occasionally we have someone in for an interview that's most likely going to be someone who was one of the course authors in the past. So you can find links to all of our YouTube videos there. You can also find links to a very active Slack channel, and I'll just clip over that real quick. We'll have post in the chat tonight the invitation to that, but we have a lot of different channels in there that are very active, and I encourage you to check out, join us there. The other thing I'll mention is that tonight's meeting is also going to be posted to YouTube probably within the next 24 hours. So if you have to leave or anything like that, you can always catch back up via that. And many of the materials that we'll be using tonight come from Coursera and deeplearning.ai. So we just wanted to give attribution to them. They developed this course that we're going through. So there may be some images or code snippets that we show from the actual course. We really encourage you, if you haven't, to look into those courses and consider joining us. And tonight we're going to be diving into the second course in a specialization offered by Coursera and Deep Learning AI called TensorFlow Data and Deployment. And we are now in part 2, which has to do with data pipelines with TensorFlow Data Services. So this is the second course, and we'll hopefully tonight get through week 1 and week 2 of this. The first week is going to be an introduction to all of how data sets are created and handled, and what pipelines are, the ETL and such, as well as some data sets that are available through TensorFlow via the TFDS interface. And Robert Craig will be going over that with us. The next week we hope to cover tonight will be dealing with taking those data sets and slicing and dicing them into the manner that you need, as well as some special ways for handling really large data sets with what's called a TF record. So George Zotto is going to be presenting that to us tonight. With that, I will turn it over to Robert. So let me stop my share. Before we start, Robert, I just want to also say, if anybody has any questions or comments as we're going through, please feel free to unmute yourself or put them in the chat, and we'll try to review them there.
Hi, can you see my screen? Just looking at the same Coursera attribution slide we were looking at before.
Yes, we see it. Yes.
Okay, great. So just one minor correction. I think this is the third course out of the 4-course specialization. So we've completed the browser-based models with TensorFlow.js, and we completed the TensorFlow Lite course. And this third course here on data pipelines is kind of a complete change of direction. In fact, if you haven't been following these last 2 courses, as far as I can tell so far, this seems like a pretty good place to just join. There's not really much that we're doing in this course that depends on the previous ones. I don't know about the 4th course. I haven't gotten to it yet. We're working through this as we're sharing it with you. So. But this third course is very much a break from the previous 2 courses about moving models to different environments other than the Jupyter notebooks that most of us have been using to learn about the TensorFlow environments and models and data sets and techniques that are associated therein. So the third course here on data pipelines is really returning back to those IPython notebook environments and showing us how to use a lot of the resources that are available in TensorFlow datasets. So this slide here is the attribution. I put up a couple of just grabbed a couple of images from the course as well as a couple of outside spots, but mostly we'll just go through a few content overviews. We'll go through a little content overview of week 1 here first, and then I'll walk through some of the actual code in the notebooks that are provided with the course. So this is an overview of the entire course 3, the data pipelines, and I guess these are the goals that we have for the course. You want to learn how to load and use existing data sets from the TensorFlow Datasets library. A lot of resources in there. Great for learning models and even prototyping new models you can often find for your task. Something that's reasonably related, a data set that can help you get started with the problem. There are also, TensorFlow also has a model hub that we will not be discussing tonight, but that is a similar repository for pre-trained models that you may find useful for your task as well. So the second learning objective of course 3 is how to explore and manipulate these data sets that are accessible from the TensorFlow data set ecosystem. And the third goal is to learn how to import your own data. So the typical data sets are really nice, but maybe you have a data set that is something that's not public, or you just have your own data. You're not going to be able to use just the TensorFlow data sets. So you want to learn how to take advantage of all the infrastructure that TensorFlow provides so that you can build efficient pipelines with that as well. And that, of course, covers bullet 4 too. And the last objective, which I think we get to in week 4 of this course, is publish and share your own data sets within TensorFlow. So if you have a data set that you've done a little bit of cleaning on and it's appropriate to go public and add that to the TensorFlow datasets repo, there is a process for doing that. So week 1 here is really just about learning how to perform ETL operations with datasets from TensorFlow datasets. And ETL we'll get into in a couple slides: extract, transform, load paradigm. And that's really the theme of week 1. So in the course introduction, in the conversation, there's always conversations between the course developer Lawrence Moroney and Andrew Ng, the founder of deeplearning.ai, and they put up a slide as one of the earliest parts of the course, and the idea was to describe the different types of data sets that are available, not just within TensorFlow datasets, but really more generally, what types of data are people doing machine learning and specifically deep learning on. And they came up with these 6 classifications here. Image, we've done a lot of work with imaging datasets. Audio, we haven't used so much in these courses, but it's another big area and a lot of work emerging there. Video is another challenge on top of image, really adding the time domain as well. We've seen a lot of examples with structured data, and of course there's the entire world of NLP with text data. I'm not quite sure why they're separating out translate here. To me that seems likely to be either audio data or text data or something. But if the purpose is to classify the different types of data, I don't quite understand this sixth category. But that's the chart that was presented. So another really useful resource for anyone who is taking the course for sure, but even anybody who might be just looking at the course from outside, you can actually get a lot of the resources directly off the course GitHub repository. Now, one thing precipitated by a discussion that we had earlier today, I actually noticed that this GitHub repo is not up to date in many cases. What's under the folders and the repo at week 2 actually includes a lot of stuff that is currently organized under week 3. So it's a little bit confusing to follow that if you're taking the course. But all the material is there in a similar state, I believe, to what we're encountering going through the course materials today. So TensorFlow Datasets is an extension onto the TensorFlow ecosystem. The idea is that you want to be able to efficiently ingest and handle and process and build models with all of these different types of data. And there is an API that has been developed to wrap around that really makes it easy to do a lot of this stuff. So the design goals here at TensorFlow Datasets, we're looking at trying to make it easy to use new datasets. Somebody maybe looking to learn text or just use a dataset that they're not familiar with. It's hard to imagine an environment really that makes it easier to get started than the TensorFlow datasets. I mean, often you can do this with one line of code. You've got the data already extracted to your system. Flexibility, standard pipeline, as I just mentioned, there's a whole lot of data sets. All these are examples. It's really easy to integrate, and the design, at least, is intended to enable very fast prototyping. I'm trying to figure out how to minimize this, but I guess that'll do it. So TensorFlow datasets, this is the source of the TensorFlow datasets information. There's a catalog here, and what we saw in the previous slide is just a really small sample of all the different stuff that's available here. These are the different audio datasets that could be useful. Some of them are music related, some of them are speech, some voices. That's probably most of them are speech and music in audio. You've got some graph data, image, a lot of image. Object detection is further images, and then various text databases such as summarization, question answering, the translate stuff, and other text sources as well. Video, etc. So we're really just going to be dealing with a very small percentage of what we have available here, and everything that we deal with in these 2 weeks is image classification data, I believe. This is also where you'll find the TensorFlow Datasets API, which is a very handy place to look up a lot of the functions that we'll be using. TFDS, some of these functions we'll go into in a bit. And now we get to the theme of week 1, which is extract, transform, load. Now, they describe the process, and this is a very standard paradigm. It's not specific to TensorFlow at all. This is a very standard data engineering pipeline methodology, and the idea here is that extraction consists of retrieving the data from wherever it is you have to go to get it, transforming is the process of doing whatever you want to do to manipulate that data to make it a little bit easier for you to, to do your actual goal. And loading is putting that transformed data onto exactly where it needs to go. So I was trying to think of a good non-tech analogy for this. Uh, one that I was thinking of was food, right? You can think of extraction being, at the beginning of the process, extraction might be harvesting crops of wheat. Transforming might be all the distribution process between the farmer and the customer who purchases the wheat, and then the customer goes home and takes that with a number of different ingredients. Maybe those ingredients came from other data sources here, and bakes a loaf of bread. And then I envision the loading process really as consuming, right? This is where you're eating the bread. Uh, that was an analogy that I came up with. I'm sure there are others. If anyone does anyone have any other thoughts on ETL from a very high level that they'd like to share? This is a very, very small group here, so I'd like to encourage everyone on the call, especially people joining us for the first time. Like, we definitely want to have an open discussion here. I don't want to be talking incessantly all night, and so please feel free to interrupt with questions on anything that we go over.
Robert, I like your food analogy, and one thing that's not necessarily intuitive about the word transform is, like, if you bring home some carrots that you're gonna cook into your carrot loaf or whatever, you don't use necessarily every single bit of the carrots. There's some parts that might be yucky and you just throw them away. And that's also true. The transform doesn't necessarily just mean like a simple one for one, like, oh, I'm going to change my date format from, year, month, day to year, day, month, or something like that. Like, no, it can be all kinds of transforms, aggregations, chucking NAs, deduplicating, whatever.
Yeah, that's an excellent point, right? You could get a date timestamp that contains information all the way down to the microseconds, and maybe you really only needed the day or the day of the week or something. So another thing that I was thinking about with that particular analogy was maybe if you want to think about this from the perspective of the user. So in our case, we are extracting data from its location, say at the TensorFlow Datasets repository, and we transform it locally after we've retrieved it, and then we load it into our models. So maybe a better description of the food analogy would be from the individual consumer's perspective. The extraction process could be as simple as going to the grocery store and buying something that's already available, much like we are doing with most of these data sets here tonight. We're just taking something straight off the TensorFlow data sets rather than extracting it from raw data materials.
My analogy of this pipeline is more like industrial. Like if you're looking for like raw materials like iron or aluminum, you're extracting them from like underground. Somehow there's a process, you're transforming them, you're picking away the metals you're looking for. Maybe you're boiling, maybe you're applying pressure, maybe you're applying magnetism, whatever it is. And then you're loading them, maybe you're making something with that material. Maybe you're making like a pod or part of a car or aluminum sheets for whatever needs we have.
Yeah, absolutely. So underneath this diagram here, just some examples of operations that are done in TensorFlow that fit under each of these categories. So at this point, I'm just going to move over to the notebooks. There are 3 different notebooks from week 1, and all of the code that is presented in the videos is either in the pre-existing notebooks, or else I added it to the bottom of one of the notebooks to for the purposes of either playing with it or for demonstrating it here. So let me open this one. See if we can run it. We'll just execute cell by cell. So this is what Lawrence likes to call the hello world of TensorFlow datasets. And the hello world is just, you know, what's the simplest example that illustrates how to use TensorFlow datasets. So here we've got a couple lines of code here just to get things started. We're going to look and check and see what version of TensorFlow we're using. And here we should still be using 2.5. And then we have the extract transform load cell. And this is a really simple example. So what we have here is TFDS was the library that we import TensorFlow datasets as TFDS. And we will execute the load method, which is hung off of that library. And it takes a number of arguments, and name and split, it may be the simplest way to call it. Actually, you don't even need the split. You could just call it with a name. And conveniently, many of the datasets are referred to by string names. And the splits as well can be referred to by string names. I believe if we go to the documentation page here, you can get a lot more information about the optional arguments that go into a TensorFlow dataset.load. We'll see a number of these tonight. Data dir, batch size, as supervised, and with info, and try GCS are probably the big ones. So I think, yeah, if you look down into these documentation pages are pretty thorough. Tells you what the deal is with each of the parameters. But the only one that's required is name, which has to be a string of the identifying the data set that you're interested in. So here, what happens when you run it? Now this, let's see, that will execute again because I'm reinstantiating the notebook. So it's going to extract the MNIST dataset, and then we'll do a very simple transform here, just shuffle. And what the shuffle 100 does is it actually considers only the first 100 elements, picks one, and then adds another element to the buffer, picks one. So it's kind of an approximation to shuffling that isn't uniformly distributed over all possible shuffles, but is good enough if you assume that your datasets are probably shuffled already coming in, and you're just looking to add some variation from one epoch to the next. And the load example here, again, is a really simple process of what are we going to do with this data now that we have it and we've transformed it. In this case, we're not going to train a model at all. We're just going to take one, which is code for just retrieve one of these items and look at it. And what you can see here is that they are actually dictionaries that come out that have key value pairs. Image and label are the keys. And you end up seeing that what this data set does is it has this image and it has it labeled as a 4. So these are handwritten digits. The MNIST data set is 28 by 28, black and white, or grayscale, I guess, with labels from 0 to 9. And that's really all there is to the Hello World notebook. So there were a number of other items that were described in the course, and
Can I add something before you move on? If you
oh,
scroll
absolutely,
up a little
please.
bit, when you downloaded it, it actually tells you the size of the data set. And there's a lot of power here, but there's also a lot of responsibility, as Lawrence mentions that. Yeah, you can do this with one-liners where you can download a data set, but just do a little bit of research in advance and make sure you have the size in advance, because some of these data sets might be quite large.
That is a good point.
This one is just 11 megs, but there's some other ones that are like a few gigabytes or even terabytes in size.
Right, you could be spinning for a while if you're not careful about that.
Yeah.
The other thing I wanted to mention, I'm glad we pulled it up here, is there's this other parameter, try GCS equals true, which is not listed in these notebooks, but is actually the best way to access TensorFlow datasets if you are running them on Colab. Just because try GCS will not download the dataset to your drive. It'll just retrieve it directly from the library every time, and it's all bundled together very easily there.
So maybe that's a good approach if your data set is huge.
Absolutely. Another thing you can do is set the data dir equals Google storage and point it to tfdata/datasets.
Nice.
We'll also use the data dir argument later. If we do download it to our system, we'll want to point that to the location of where those files are so that for future operations, we'll know where to find them.
Cool.
And Robert, I think, I don't think we've seen it before, but we'll see it a lot in this course. A really powerful thing that we just got was this is a data set, not a data frame like we've seen many times. So this is a tf.data.dataset object that we're dealing with, which is a very powerful, we'll learn it's a very powerful library.
Yeah, I was going to talk about some of the properties of these data sets in a bit.
Right.
So a couple things that I wanted to add to this notebook to demonstrate some things that were presented in the course videos. So, and we'll be mostly doing the extract and transform processes here. Define a few constants, num samples 100, epochs 3, batch size 16. And again, we're going to do this very simple hello world type extraction operation. Now, I also wanted to point out that using the method name load here is a little bit confusing in the context of ETL, because this is really the E, not the L. And when we look, we can do this even simpler without a split. When we don't call a split argument at all, it's just going to get the entire data set. So I have DS and dataset 1 here, and dataset is what's called a prefetch dataset. And if you go through the course videos, it's actually shown as an options dataset. So I assume that the library has changed a little bit, and this may be a new data type. All of these different dataset types are subclasses of the tf.data.dataset class. But this prefetch dataset here consists of, again, your image 28 by 28 by 1 and a label. It also will give you the data types. So it tells you that your image is unsigned int 8-bit and that your label is a 64-bit integer. So to go down, drilling down a little bit more into these data types, I threw in a number of other transform operations here just to show different things that you can do. You can chain them all together. You can say dataset.shuffle, .repeat, .map in that type of syntax. But here I just thought I would show what the data types are that result from every step. And you actually see that TensorFlow has built in all these variety of, there's a shuffle dataset and a repeat dataset and a map dataset and a batch dataset and a prefetch dataset. And it's all very confusing. But every single one of these things is really just an instance of some specific type of TensorFlow dataset. And if you look at the TensorFlow, which see, I think if I go into this one, I'll just search it up here. If you go into the API documentation on the dataset object itself, you get all these different methods that you can apply to a dataset, and many of them yield each of these different types. Like if you .batch a dataset, you'll get a batch dataset. If you put a map on a dataset, you'll get a map dataset. And it's a very powerful, very flexible approach that allows you to combine various transformations pretty effortlessly. I will say that every time I've worked with datasets and done these operations, I still get a little bit unsure and want to check the data types at each point and make sure that I'm getting the right size, that my tensors look right at each step. But the capability is definitely there, and it really streamlines the appearance of your code.
Robert, sorry to interrupt here. Because I'm struggling with this kind of TensorFlow data set.
Sorry, Vladimir, do you mind speaking up a little bit?
Sorry, yeah. Can you hear me better now?
Barely.
Barely. Okay, so maybe it's again my microphone thing. Is it better now?
Yes.
Yes.
Okay, sorry. My kind of speculation is that it's not about the type. So the type, when you see this map data set and repeat data set and stuff, it's about a record, how the data set will be processed once the actual execution starts. So you have this kind of TensorFlow computation graph that is built. So when you write this code, this batch map shuffle, and then let's say the example that we started, this basically creates a computation graph that after the Python code is compiled, basically the computation graph is created. TensorFlow creates a graph of the sequence of the execution steps that are going to be executed once the actual execution starts. And this is not necessarily the order in which you see the statements in the Python code. The reason for this is that TensorFlow dataset is intended to provide a parallelism of the data input by pulling data from various sources. I mean, from the disk, let's say, but this is done in a parallelized way in order to prevent this called data input bottleneck or the data input bound to the GPU, because the GPU needs data all the time. If the CPU cannot provide fast enough the data, the GPU has to wait. As a result, the time is much more than it has to be. So in order to basically synchronize the operation of the CPU and the GPU so that the GPU has data all the time, this TensorFlow dataset provides this kind of parallelization of the feeding rate of the data, and arranges this via this dataset class and its methods. So the dataset, the different datasets are actually not different types. Okay, they're different types, but they just point to the same data, how it's going to be used at the time when the execution starts. That's at least my interpretation. I don't know whether it became.
Yeah, I agree. That's very well said. It really is not altering writing
The data, right?
of any data in memory. It's just a representation
Right.
of what's going to happen.
Sorry.
Yeah, and the point about the getting your data to the GPU in time is very important as well. That's one of the reasons why the prefetch is here, actually, that enables you to be moving something to the GPU while you're processing something currently on the GPU. And there was my link to the dataset page. So list builders is another method that's presented in the course, and it's shown as this little pop-up graph here where you have TFDS in the middle and video, image, structured text. I don't know if you all can read this on my screen share. It's a little bit small even on my own screen. But this is a graphical representation of all the data sets, or at least a subset of the data sets that are available in TensorFlow Datasets, TFDS. And what you actually do though, when you run it, you don't get a nice picture like this. You just get a list, alphabetical list of all the names of the data sets. So we see our old friends here: MNIST, Iris, Kitty, Fashion MNIST, all the usual suspects.
There's a lot of them. Different types as well.
I've noticed that this first 2 weeks at least of this course seems to hit all of Lawrence's favorites, right?
Right.
Rock, paper, scissors, horses and humans.
Cats versus dogs.
Cats versus dogs. We got MNIST. We got Fashion MNIST. We even get multiple shout outs to the diabetic retinopathy data set, which we're not going to work with, but is something that Google has taken pride in including as part of TFDS. So another really useful thing to take away here is that you can view the metadata of a data set, and having access to metadata is super important for a variety of reasons. But really, you want to have you want to know what version of data you're working with at any time, and you also want to have some sort of background that tells you where exactly this data set came from, what's its history, who collected it, etc. So this is all the information that can be available in a dataset info. I would imagine that there are probably datasets that don't have all of these things. I know that some of them don't necessarily have splits. They probably all have a name, and maybe many of them have descriptions. And how do you get this information? Well, you usually just call tfds.load, and here the special parameter is withInfo equals true. And when you do a withInfo equals true, instead of returning just the dataset object, you also get an info object. And when you print the info, you get this tfds.core.datasetInfo, and all these different features here that we saw graphically right there, you can drill down and see what the information is. So in the case of MNIST, we have a version number, a description, homepage, which really is a link to much more of the history behind this data set. And we have this is a really important one here, is the features dictionary that tells us what exactly we have, what we're going to be looking at, and what they are called, and what the shapes are and data types. We also learned something about the sampling. We have 70,000 examples, but they're split into a couple different named splits. If you get the supervised version, which we'll show in a bit, then you'll get an image and a label. And here's some of the history, and it looks like redistribution info must be blank. So we're also shown during week 1 how to request different versions of datasets. So if you want a specific version of MNIST, the course tells you, well, you should type in MNIST, and then you get to put in the version number here. And what you have here is the 3 numbers. This could be 3.0.1 is the version of MNIST that will result from this call. But this is the major version number, the minor version number, and the patch number. And essentially the major version number is going to change anytime there's any substantive change to the data itself. The minor version number will change whenever there is a new feature added, I think,
Yeah.
to the data set. Maybe something new is added to the info. And the patch changes, I don't remember what that is. I think it's just if something is corrected, or I think it's usually there to replace an old one, not to supplement it. However, I did notice that if you try to get any other version of MNIST, it will fail. And so if you request MNIST version 2, you'll get an exception. Dataset MNIST cannot be loaded, only 3.0.1. And I found this with a couple of other datasets as well. So I assume there must be examples that you can get multiple versions of, but I didn't see one yet. Another variant of the way that you can call this function, tfds.load, is you can call with as supervised equals true. And this is a convenient way to retrieve a data structure that may be more ingestible by your model. So, or by your pipeline at least. So this will convert it into tuples rather than the key value pairs. So if we load a data set, just the standard call, and then we load a supervised version with the supervised call, we see that the standard call we get inside our prefetched data set, it's actually a dictionary with an image and a label for the test. And then the train split is the same thing, a prefetched data set dictionary containing an image and a label. And if we look at the supervised version, the test prefetched dataset is now just going to be returning tuples to us. So the shapes here are going to be a 28 by 28 by 1 tensor, and the label is simply a scalar. When we look at the standard split names, we have a couple easy ways to call splits from TensorFlow datasets. tfds.split.something or other. You do have to check to make sure that they exist. In the case of MNIST, you don't have a validation data split, so if you uncomment this line and run something like that, it will throw an error. It doesn't check that for you. At the end of this video in the course, he also showed you how you can how this works under the hood. My impression is that this is the way that you used to have to interface with this library when it was newer. You would instantiate a TF dataset builder object, then you would have to download and prepare, and then call with a split argument if you wanted. But you eventually get the exact same result here that we had in the in this call.
Lawrence mentioned that you can do some more advanced things with this custom builder or this TFDS builder. I didn't see any more advanced examples than the basic ones, but is it just showing us what happens under the hood, or how actually things work under the hood, or
that's how I'm interpreting it at this point. I would imagine that there are probably examples further in that maybe you're actually dealing with these objects. But right now, he didn't show anything further beyond these 3 lines.
Yeah, maybe if you want to make like some kind of custom pipeline, the default TFDS load doesn't offer you. Maybe you can do that.
Sure. So are we done with this notebook here? I'll close it.
Yeah, go for it. Thank you, Robert.
And I guess I have to manage the session though. Terminate this one.
Because you're using GPU, I guess, right? That's why.
I think the free version only allows you to use 1 GPU running notebook at a time. Is that right?
Yeah.
So this one here is a copy of horse or human. And here he's just going to show us a slightly more advanced examples, but really not too much more advanced than what we saw previously. So,
Robert, do you mind closing that table of contents and just zooming in just a tiny bit for people watching us on a smaller screen? Just Control plus. Or
is it Command plus?
Command plus, or just to, yeah, perfect. Perfect. And you have a download bar at the very end. You can close that as well to save some real estate.
This guy?
The one underneath it.
Oh,
there you go. Perfect.
So this is actually going a little bit beyond the purpose of this course here. This cell contains a very simple convolutional neural network, and it trains it for multiple epochs. It looks like it's about half done already, though. So again, we're just going to load up TensorFlow, load TensorFlow, import TensorFlow as TF. We're again going to import TensorFlow Datasets as TFDS. If you are pulling this off the GitHub or running the course, you'll actually have to manually comment out this line. I don't know. I'm assuming that this is some library that used to exist that no longer does. It's not referenced anywhere later in the code. So what are we doing here? Data equals tfds.load. Again, we're going to extract the horses or humans is the name of this data set. And is this Lawrence's data set? Did he create this one?
Yeah.
Yes.
Yeah. That's what I thought. He's the mastermind of this one and the rock paper scissors, right?
He has a lot of experience with computer graphics. Yeah.
Yeah. All right. So split. We're gonna get the train split here as supervised true. We're gonna actually call tfds.load multiple times and get validation data separately. Here we're doing some transform steps in the next block. And what are we doing here? We're taking the data, again we're going to shuffle it with this buffer that's 100 long, and we're going to drop it into batches of 32 examples each. The validation data we don't need to shuffle, but we will also want to batch it in the same size. And right now we're looking at a convolutional neural net model which is where we're going to put this data eventually. When we fit, the trained batches are going to go there. And this is an example drawn directly from the TensorFlow in Practice course that a number of us did when we first started this Deep Learning Adventures meetup back in the old days. There's a link. If you're this link right here will actually take you to somewhere up here. If I can. Can't get to the windows that I want. I can't remember what the command to move tabs across. Is it like command left or?
For me, it's Shift Tab.
Shift F?
Shift and Tab.
Shift Tab.
Sorry. No, let me try it again.
I think it is something tab. Right.
Control Tab.
Yeah, that's it. Thought I think it must be this one. Yeah, this is the notebook that he was referring to way back from the second course under TensorFlow in Practice, where we were using fashion MNIST, and probably the horses and humans one is down in here too. And the reason I wanted to come look at this is actually there's an interesting contrast to be drawn here that he goes into about the difficulty of or about how much easier TensorFlow datasets makes it getting your data, right? Instead of tfds.load and one line or a couple lines, and we've already extracted and we're starting to transform our data, recall the process that we went through back in this notebook. First of all, we run this wget thing to download a zip file from some website. And then we have to import zip file, do some processing, extract these to files that we download and install somewhere on our system. And then we had to go through this whole process with an image generator, and I think it's called image data generator, somewhere way down in here. Data pre-processing, the image data generator, and we defined rescales, and so this process becomes a lot easier with TFDS. And that was really the point of comparing back to that previous notebook.
And just to be clear, Robert, he could have done the load of the train data set and the validation set in one line. He chose to show it as 2 lines, but he could have done it all in 1 line.
Sure.
Where? On the other notebook?
On the one, no, the one we're going through now.
Oh, right. This could have been done in 1 line.
That could have been, both those lines could have been combined. Yeah.
Mm-hmm.
If you list both the splits with a comma, then you can, it'll put them both out.
Right.
Into a tuple of data sets.
Yeah. But I'd like the reminder you gave us, Robert, of the zip file, the extract, and the folder, and folder structure, and image generator, and all that. That was interesting contrast.
Yeah, I'm pretty sure also George will be getting to some of the ways to do these splits and define them with kind of custom splits during week 2.
Yeah.
Cool. So, and then he also gave another very brief example with fashion MNIST during the course, just showing how you can extract this stuff really in 1 line. And this is that exact thing that David was just talking about, how you can get, if you just give it a list as a split instead of 1 split, then all of a sudden you can get, here we're actually getting 2 tuples of data, right? 1 for each split, and because we called as supervised true, we're getting an images labels tuple of each one. The only other portion of week 1 in this course was the exercise itself, and you can actually access the exercise here on the GitHub website. One of the cool things about this course is that from the GitHub websites, you always have these collab links where you can almost immediately start to tear apart the code and start playing with it and figuring out how it works. So there's little exercises here, and you put your code here, etc. I don't think there was anything too interesting about this assignment. Some of them you have to, they had to edit them after the fact to make them smaller to pass the grader. But I think we've gotten to the end of week 1, unless there are questions that people want to address.
So Robert, can you go back to your horses versus humans and where the actual load happens, the output from that?
This one?
Yeah, so where the output for that at the bottom. So I often see this when I use TFDS datasets that pull down. You see that nice, that red, and that normally looks like something went terribly wrong. But it's not real, and I just wonder if anybody has any explanations for what it's really telling us.
Yeah, I'm wondering that too. I've noticed that before and never really thought to ask.
That's maybe something we should follow up with Lawrence with.
Yeah, I think he briefly mentioned it. He mentioned that after downloading it, it's shuffling it and then writing it to disk, which kind of begs the question, why are we shuffling it again after we read it from the disk?
But I think I've had multiple experiences where I'll be running something in a notebook like this and just kind of casually keep an eye on it, and oh, you've got a red bar here that's not finished and a 0% here, so I just assume it's not done.
So it's consistent like that. Okay.
Yeah, it happens a lot. And it may just be a function of IPython and the way the loads they don't work well together or something. I don't know. But I do find it normally doesn't mean anything.
Yeah, that is
Hey,
a good question.
David, you know what? I've seen that too. The reason why it's red is because, right, I think this is using like TQDM to do the pretty little progress bar.
Yeah.
And so red means that it completed, well, without actually erroring, right? It means that it completed without executing the number of expected iterations.
Okay.
Okay.
And what does it mean when it's 0%?
So what you're saying, Ted, is that the color choice of red is just a TQDM default setting?
No. I'm saying it's doing red because it successfully did whatever you asked it to do. But if you look, it thought it was going to take 1027 loops, but somehow it got to the end of the file, the end of the data set, the end of the whatever it was iterating over after 906.
Yeah.
So it overestimated the size of the data set or something, or the process.
Yeah, and I don't know if that might have to do with like train test split where somehow it had the wrong number. It was expecting the full thing, but it only got 90% of it.
I think it
And
has something, I think it has something to do with the fact that when you download it, it's compressed. So if you see above, it says download, this is the original size, and then you uncompress it. And maybe it has an estimate of how big the file will be uncompressed, but that was just an estimate. So maybe it's just a little bit smaller than it expected.
yeah, but it's a good point because I've definitely seen that too in notebooks. And there was one time when I investigated and I actually got to the root of, oh, there was just something going on where basically there really were 906.
Okay.
But for some reason, the way the code was written, TQDM was somehow being told to expect 1027 iterations.
Okay. And I recall an option where because I've shown these things other places and I didn't want this to be looked that way. And I recall there's an option you can turn off, you can basically make it quiet and it'll turn off these outputs.
Cool.
Yeah.
Can you
But
scroll a bit
I've
to
never
the
understood why.
That option is
load option probably?
Yeah, I think
just
it's something you call
this function.
No, it's not in there. You have to call it
speak
on TFDS before you do it. I'd have to look back. I can't remember. I'll try to find it while you're going through the next stuff.
Can you scroll a bit to the right, Robert? What is the difference between the first and second shuffling? Is it the training test or is it? Okay. Yeah.
One's training, one's test. Yeah.
Okay. So maybe it did it so quickly that TQDM couldn't keep up with TensorFlow and didn't even register. It went under the radar.
Yeah, I mean, if I had to guess, somehow the train is 906 out of 1027 and the test is 111, and it somehow got it got the total number, even though train is really only 906. And I don't know, but you're definitely right. I have seen this multiple times. And yeah, when you see red at first, you think that's bad.
I threw the thing you have to set to disable the progress bars.
Oh, cool.
All right.
But anyway, just so if anybody else is wondering, if it really did error, you would get an error message. It would be more than just a red progress bar. So the red progress bar, just without an error message, just means that it didn't do as many loops as it thought it was going to, but it did complete successfully.
Cool. Thank you, Robert. Thank you, friends. This was an interesting week and a lot of content. Cool. So just as a reminder, we're still in course 3 and we're going to cover week 2. after week 1 that Robert just covered for us. And before we talk about week 2, which has a lot to do with the split API, I just wanted to share a resource that the course mentions as well on splitting and slicing and lists and tuples in Python. This is used extensively in the split API, and just a basic reminder. So let's say we have a list in Python, a very basic list. If we want to access a specific subrange or subset of that data, we can use this semicolon split arguments or syntax, where we are saying that start from index 1, everything is 0 index in Python, and up to and not including the last index. So this would be, so 0 is the first index, 2 is the 1 is the 0th index, 2 is the first index, or 3 is the element in the second index, and so forth. You can do this for tuples as well. You can also specify the number of steps, how many you want to jump. So you want to go from 1 to 4 with increments of 2 instead of increments of 1 each time. This confusing syntax basically says that start from the beginning to the end, but go in reverse order. That's what it means. So semicolon, semicolon -1 is just sorting the list or array or tuple in reverse order. Yeah, you can do this for tuples as well. Let me see if there's anything. Yeah, there's some other ones as well we're gonna see. If you want to traverse the list in reverse, or if you want to work with the end part of a list, there's ways to do that as well. Cool. I think the best way to explain the splits API in TFDS in TensorFlow Datasets is through a notebook. So let me reconnect here. Cool. Let me zoom in a little bit more, and I will open this at some point as well to see where the data is and how is it structured. So we're just importing TensorFlow and TensorFlow Datasets, and I'm running Colab here. 2.5, yep, that's good. And we are loading the MNIST dataset, the handwritten digits dataset version 3, any subversion or minor version and patch, we don't really care. Just give us the latest one, basically. That's what this means if you specify star. And we are specifying in the split argument this list. And this list is a list of names that this dataset has already built in it. So it has a training subset or our dataset as well as a test dataset. So we're not specifying with supervised or supervised true. So that means that we're not going to get a nice separation of images and labels. We're just going to get our dataset as it is. And we have to do internally the split. We internally have to figure out which is the image part and which is the label part. So this is downloading from TensorFlow dataset repository. Maybe I should try this. Try GCS true next time. It will be faster. And I got a green bar this time. And it will actually tell me where my dataset was downloaded. So this was downloaded and prepared under here in Colab. So if I go under Colab under here, under folder, go up under root, right? So it says TensorFlow Datasets, that's the name. That's where I am. MNIST is the name of the dataset I just downloaded. The version is 3.01. And you see this structure here. You see some JSON files and you see some TF records. I'm going to cover them later. I just wanted to show you where the data lives now that I run this TFDS load. Cool. Minimize this a little bit. There you go. Or even close it so it's not confusing. And if you see, we printed here the size of the training dataset and the test dataset, and there's 60,000 training and 10,000 in test, for a total of 70,000 images. Cool. One other thing we can do is we can do what is called concatenation, or we can combine the different underlying data sets in one call. So for whatever reason we wanted to combine train and test, we can do that with this syntax. So this is like a string syntax. And this means that TFDS will look at MNIST, the latest version 3.0, 3. Whatever it is, latest version. It will take the training and the test subsets and it will combine them into one larger set. So if we load that, this will not load from the TFDS repository. It will figure out that it's local, I think, on our machine, and it will just try to combine both sets in one. So this should run faster. Yep, and you shouldn't see this downloading and preparing. Good. The other thing is, let's say we wanted only out of the training subset, we only want the first 10,000 records out of 60K. We only want 10K records or XK. So we can do this with this, what's called this up to split syntax or slicing syntax. So the way you read it is up to and then a number, is just if you remember from Python. So again, nothing else has changed. I just changed the split argument, and that has my first 10K records. The other cool thing is you don't have to specify a hardcore number. You can specify a percentage. So if for whatever reason I want maybe 10% or 20% or 30% of my training subset, I can just do up to and then a percentage, a number and a percentage. So I have 60K, 20% of that is 12K records. Cool. The other neat thing that Lawrence,
George,
yep.
One thing that kind of surprised me when running these lines here is how long it takes to execute some of these lengths of these lists.
Mm-hmm.
I would think that once it figures out the size and shapes of the objects in memory, shouldn't it be like just an O of the number of records calculation at the most to?
Yeah, that's a good point. I don't know if it does any randomization in the back end, or I think it's trying to keep track of all the metadata as well behind this data set. So it's giving you a tf.data.dataset, so generating that as well.
Yeah, it is generating it, right? The load is just kind of telling it what to do, but the combined is actually forcing it to turn it into a list. It just surprised me how long that operation takes.
Yeah, a few seconds, right?
Yeah.
Cool.
Yeah, so for what it's worth, I think the creation of the list is the slow part, not the length and not the generator.
Oh, this part. Yeah. Because you're converting it to a list and then getting the length. Yeah. We can.
But each list append should not depend on the length of the item that you're putting, right? You're just adding another memory address to the length of to a list that's only 10,000 long.
Yeah, I don't know the internals for Python as well as I know some other languages, but if you have a list that you append to 20,000 times, it's probably creating 20,000 different lists and throwing away the first 19,999.
My understanding is that list append is 0.1 on average. That maybe you'll occasionally double the memory footprint of the list if it grows too big beyond a certain point, but that most appends are just using that next block in memory and not touching the rest of the list.
Okay, so it's in place except when you happen to run out of memory and then it needs to copy it to a new location.
Yeah, like I mean, a dictionary does work similarly as well.
But why are you using append like
time?
Yeah, sorry, why are you saying append? Like I'm just storing this into different arguments, so I'm imagining they'll be in different places in memory.
Well, I was just thinking that while the list is being generated, it's adding one element at a time to that list before it calculates the length.
Yeah. And I removed that argument, right? I'm just running the tfds load, and that runs in like less than a second. But yeah, this argument is basically loading all the data in memory, then converting it to a list, then calculating the length. So yeah, this is
Right. So to Robert's point, if you remove the len part, I think it'll take the same amount of time.
yeah, for sure. Yeah, yeah.
'Cause that's not the expensive part.
Actually, printing the list would.
But I don't want to print.
No. Or yeah, if you just do nothing with it. Just assign it to a variable
Assigning it
instead
to
of
some
printing.
other variable, yeah.
Yeah. Cool. So let's find a better way to do this then. I would imagine there would be some kind of length or key or size within TFDS. I didn't say that. Cool. For the next item is some more advanced splits we can do. And I think that's best explained in this slide here that Lawrence explained. So let's say we want to do what is called k-fold split. So we want to expose our model to a given data set. Let's say we have 70,000 images, but we want to try slightly different models, or we want to try the same model, but expose it to different training and validation, or training and test data sets. So let's say training and validation in this example. So in blue is our training subset, and in red here we have our validation subset. And when we do the first fold, we want to expose our model to let's say 10% of this combined 70K records will be our validation set, and 90% of it will be the training. On the second fold, we want to shift the validation set and so forth, so that each time we do this, we expose our model to a different collection of training and a different collection of validation data and images. So the way that you're doing this is actually within the load command itself, where you are specifying basically variables here, and you have a for loop that goes from 0 to 100, jumping 20 units at a time. And then for the validation, you are just going from 0 to 20. That's the first red one. The second one would be 20 to 40, 40 to 60, 60 to 80, 80 to 100. So this command will actually generate 5 different data sets. So this val.ds will be an object that has 5 elements in it, and each element is actually tf.data.datasets. And then similarly for the train one, we need to pick out now the complementary data set of this 70K. So I found that very interesting. So we do that here. We run val.ds and train.ds. See, that didn't take a lot of time. And if I take a closer look at validation dataset, you see it's a prefetch dataset shapes, but the length of it is 5. Same with the length of the training dataset. And if I just take a look at one of them, this is an independent dataset on its own, so I can do something with it. And the size of it is 48,000. So this I didn't convert to list, so this was faster. Maybe you don't have to. Like for me, this was very quick. Cool. The other neat thing that you can do is, what if you wanted to do, you have a collection of data. What if you wanted to take something from the beginning and something from the end? And that something could be variable. Let's say you want to take 10% of the records from the beginning of your data set and last 80%. So basically just leave the middle 10% in it. So the way to do that is, and this could be also from different subsets. Maybe you want the first 10% of the test data set and the last 80% of the trained data set. You can do that as well in the syntax. So what we're doing here is from the test subset, we're just taking the first, and I mean first because we have the syntax here, 10% of the records. We are combining that, this plus means combine it with the training data set, start from the end, and give me the 80% of that data set. And let's see how many this is. So we know the training one is 48,000, right? The test one is 10,000. No, the training one is 60,000. So 80% of that is 48,000. 10% of 1,000 is 1,000. So 10% of 10,000 is 1,000. So 48 plus 1, 49,000. Let me see if this runs faster. There you go. This runs much faster. You don't have to convert it to a list. Just do len of that data set. That's the difference. Cool. Let me zoom out a little bit.
And I guess they could have done len on the initial data set right after the load, right?
Yeah.
Just like you did here.
Yeah. So yeah, I'm pretty sure, I mean, this object has its own method of calculating its length, like a very efficient way, instead of converting it to a Python list. Cool.
Yeah, maybe converting it to a Python list forces it to resolve those objects.
Yeah, exactly, yeah.
Into arrays or something.
Yeah. Cool. So next we're going to take a closer look. If you remember, when we downloaded the data set, we had this shards and this records and this JSON object. So we're going to take a closer look now at this file structure of TensorFlow datasets. And based on how big or how small your dataset is, you might see multiple files like this. But usually if you run this under Colab, this will be under root, under TensorFlow datasets, the name of your dataset. In this case, we're just downloading a NLP dataset, a text dataset from news headlines from CNN. The version is 1.0. And then based on the splits that, or the subsets that this dataset has, you'll see multiple records, at least one record for each one of them. So if you see for train, we have 16 of them, and they're counted as 0 out of 16, 1 out of 16, and then 15 out of 16. And then for test, we have 1 in the very beginning here, 0 out of 1. And then for validation, we have 1 at the bottom here, 1. We also have some dataset info JSON objects as well, or files that we're going to take a closer look. Yeah, before I do that, let's do it with this MNIST because it's very simple to take a look. So let's look, for example, at dataset.info.json as well as image.image.json. I'll make this bigger and zoom in. So image.image.json is basically a description of how our data is encoded. So you saw we did different splits. We got 48,000, 10,000, whatever number of records we get. But if we wanted to inspect one record at a time, what is it? And this image.image.json gives us an idea of what we're looking at. So we're looking at an image, and what is the encoding? JPEG, PNG, any other encoding that you have for images, as well as what is the shape. This is monochromatic, right? This is black and white of 28 pixels by 28 pixels by 1 channel. And if I wanted to get a little bit more information about the data set itself, and I think Robert covered this. So what is the title of this? Make this bigger. The description, there is a size, perfect. The size of it, probably in bytes, right? So 11 meg, perfect. The URL, name, this schema is important of how it's structured. 28 by 28 by 1 of integers. Then the splits, we have a test split, number of bytes as well, labels, number of examples, train split, and if you use this is supervised keys or with supervised true, then you also get this separation of images and labels and version.
So this version of the dataset info, I think, is a lot more detail than the info objects that you just get when you call with info equals true.
Or is it? I don't know. Could be.
Right. We didn't have. I mean, or maybe it's just that the format is confusing me, but I don't remember getting things like num bytes and num shards.
Or missing, yeah, but it's
I guess when you're doing that, you've already extracted it, right?
yeah. This comes with a data set, so the data set authors included it. I don't think it's generated on the fly. This is already included with the data set. It's pre-calculated, I would say. Right, because it has like some statistics of what's the maximum value, what is number of records that don't have missing values. You know, this could take a while to calculate. You know, label, what's the max label, number of bytes, shards. Yeah, it looks a bit more detailed, but maybe we didn't explore that method in detail, right? The .info.
Maybe.
Cool. And then the other thing I wanted to cover is what if we want to take a closer look at this MNIST train.tf record or test.tf record. And if you remember back in the days when we did Kaggle competition with structured data, we worked with Higgs boson detector, and that had a lot of features. It was structured data, but had a lot of features that used TF records, and that was my first really deep dive into TF records, and I was trying to understand. I kind of got the gist of it, but hopefully after today's presentation, we'll have a much better understanding of what's inside of this TF record. So if I wanted to look at what's inside one of these records, I would just for you know, data exploration purposes, I would just point at one of them. So in this case, I'm just pointing at a file name of very specific one of those multiple shards, as they're called, that you saw. Then I would use this this generator, this class tfdata.tf record dataset with that file name. That'll be pointing at my raw data, what it's called. If I want to take a look at one record of that, I have thousands of records. I'm just going to look at one of them. And this REPR, this representation wrapper, gives me a conversion. I forgot to say that these TF records are actually in binary format, 0 and 1. So if I wanted to look at that maybe in hexadecimal or some other format, this representation does that for me. And if we do that, we're going to get something like this, where you are looking at a tensor. We don't really know what's the shape of it. You can specify how it's, let's see, we can specify this later, but for now, this is just characters for us. And B means binary, is just represented in hexadecimal. So we have a new line, some binary characters, some binary character, new line, some binary character, some binary character, then image. Some of it is readable, most of it is, non-readable or doesn't make sense to us because it's hexadecimal. And then a lot of it, and this is just one record. So we're looking at the raw data of one image of 28 by 28 by 1. And if you can tell me what number that is, you are the best. But you see here, we don't know where the image starts. We don't know where the image ends. We don't know where the label starts. We don't know where the label ends. We don't know what the label is. We don't know what the image is unless we decode this, right? Or show it. So let's take a closer look at this example. So another notebook. Let me connect. Okay, reconnect. Good. So I have to terminate my other one. Reconnect. Good. So same load with info true. I'm not specifying any splits. I'm downloading everything basically from MNIST. And this now should have my data under here.
Can you use the eyes for us just a little bit?
Say it again. Make it bigger?
You got it. You got it.
Perfect. Yeah, I was going to. So if we're under root, the name, TensorFlow Data Sets MNIST, this is where our data is. Great. and then zoom in again. And if I wanted to point to just one file, I can do that. This is updated in the notebook. This was 3.0 and it was running for me, but this is not 3.0.1. It was a patch update after the course was written, I guess, or after the notebook was written. So if I want to take a look at it, you see this shape, NumPy. I don't know if there's an easier way to copy this and add maybe text. Text, there you go. So that's the same text that we saw before, but as you can see, it doesn't make much sense. So the way that we are supposed to read this is, if you remember, we had, let me go back. We had this dataset.info.json. Sorry, there you go. That tells us how this data is structured. So specifically, I'm interested in this feature object here. So you see we have an image and a label key. And this is how my TF record is structured. So when I need to parse data out of it, I need to parse data by an image, and then I need to parse data by a label. That's what consists individual TF record. So having that, I can create what is called a feature description, which is basically a map that describes how my data is structured within this maze here. And in this course, so I know that I have an image and a label key. And in this course, Lawrence mentioned this fixed length feature, which is basically, I'm going to go look at documentation as well, but I know that my images and my labels are a specific length, right? So, or specific size. So I can use this fixed length feature to basically allocate memory on my computer for storing an image and for storing the label. Now, the next thing that was new in this course was this TFIO. A bit more. Oh, perfect. I love the documentation. This parse single example. So this parses a single example proto. And what that really does is it takes raw data, as we saw from before, and given this feature description, it will try and parse out the images, the image part and the label part, so that we can take a closer look at it. So we're defining this custom function, parse function that takes an input as raw data. And we are telling it what feature description to use, which we've defined here. And we're just telling it, can you just parse it out for us? Instead of giving us a long list of hexadecimal numbers, can you parse it out? Can you parse out the image part? And can you parse out the label part?
So I was a little bit confused about this. When you look at the feature description that we have defined there, we're not telling it what the size of those images are, right? You're passing an empty array to fixed length feature.
Mm-hmm.
Did you figure out how this is actually doing the parsing?
So I don't think the size matters. All we know that is the dimension of it matters.
Are there some kinds of stop characters or something that signify when image is ended and label is?
Yes. And if you actually look at this one, well, it will make sense after we look at this TFIO parse single example output. Then when we go back here, I think that TFIO will make a little bit more sense. Sorry, I'm gonna create. Sorry, zooming in, zooming out. I'm gonna create a text field, not a code field. There you go. Perfect. So before, remember, it was just TF tensor and then hexadecimal. Now we have an image, which is the image part. ends here. There you go. Okay, I'll separate it like that. And then we have a label, which we can actually decode, and it's an NumPy. It's an int 64 and has the value 2. So at least we know that the label for this record is 2, and this is just the content of the PNG image. Now, if we go back to our original, before using this IO parse single example, and if we kind of look close, there's an image key here that's in the TF record. That signifies the beginning of the image, and at some point it should end here. And then there's a label as well. Oops, sorry, I didn't want to do that. There's a label as well. So without this feature description, we're just getting the raw combined image and labels. And this feature description is saying, I'll parse out the image part. I'll parse out whatever you tell me. So you better know what the structure of the TF record is. You better know these keys. This fixed length, all it says is that all the images are expected, to be the same, I want to say size, but for sure shape. And we know that they're 28 by 28 by 1. Size, I do not know.
Yeah. Somehow I totally missed the words image and label hidden in there.
It was part of the quiz for this week. So yeah, at least you can see now that this is image 2, and this, if you convert it with the library to, if you display the library that converts this to some readable format, you should see hopefully a digit 2. Yeah, so this fixed length feature, configuration for parsing a fixed length input feature, shape of input data, data type. This was an interesting one. This was like a placeholder for me. That's how I describe it. The parsing example as well has segmentation, very short, has some tutorials. Be nice if I had some more examples though. So there's fixed length feature and there's variable length features as well. We haven't seen variable length features. I'm curious what those look like. Then the TF data set. And the last thing is for the
variable length features might be text, right?
Yeah, we don't know the length yet. And the last thing I want to talk about week 2 is that in the exercise you're supposed to download a trained model. You're supposed to do transfer learning basically. If you're downloading a MobileNet, which is pre-trained on ImageNet, and you're supposed to fine tune it on humans, I want to say. I don't remember. I did this. I may remember. I'm not going to GitHub because GitHub is a little bit outdated for this week, and cats versus dogs. That's what it was. Cat versus dogs. Okay, it was one of the popular ones. So you're supposed to use a pre-trained model, a MobileNet, and it's supposed to fine-tune it on cats versus dogs, which is a data set that you can access from TFDS. That was the exercise for this week. Let me see what else do I have here. Yeah, you just have to be careful a little bit with the size because this model expects specific, as you know, right? Specific width, height, channel combinations. And for me, I don't know if you did a notebook, but for me, the training part didn't even run. I couldn't run it for one epoch. I think it used a lot of resources. And for whatever reason, this Coursera Jupyter Notebook instance is not strong enough. Cool. That's all I had for week 2. I think we're gonna wrap up here if there are no more questions. And yeah, looking forward to week 3 and week 4. There's a lot more content coming up, as Robert and David mentioned. Cool. I'll stop sharing at this point.
Yeah, we may struggle to complete 2 weeks next time.
You think so?
Get a lot of content.
Okay, then we do one and we do the other one the next week. It's okay. Cool. I'll stop the recording for our YouTube friends. Thank you for joining us, friends. Feel free to subscribe and hopefully join us in person or online one day. But I'll leave the floor open for everybody else.